Good morning, distinguished colleagues and conference participants. First, I would like to thank the organizing committee for the opportunity to present our work in this academic forum. My name is Pedro Marquez, from the Division of Graduate Studies and Research at the Tecnológico Nacional de México, Instituto Tecnológico de Chihuahua, Mexico. This work was prepared in collaboration with Carmen Garcia and Abraham Rodriguez. Today, I will present our paper entitled CRLL-X, a Controlled Mission Language for Multi-Robot Logistics, which proposes a deployment-oriented controlled mission language for transforming human mission intent into auditable robotic execution. In this presentation, I will introduce CRLL-X, a controlled mission language for multi-robot logistics. The starting point is that, in collaborative robotics, a mission is not just a sentence that sounds clear to a human operator. A phrase such as, "reserve the dock and carry pallet 7, contains hidden assumptions about actors, objects, availability, priorities, resources, timing, and execution policies. If those assumptions remain implicit, the system cannot reliably parse, verify, execute, or audit the mission. CRLL-X proposes an intermediate layer between human-readable mission descriptions and robotic backends such as simulators, symbolic planners, and ROS2-oriented execution stacks. The goal is not to replace those backends, but to give them a structured, mission-level representation. The presentation emphasizes three ideas: syntax, semantics, and evidence. In other words, CRLL-X makes mission intent readable, formally structured, and experimentally inspectable. The central problem is the distance between intent and execution. In a warehouse or logistics environment, an operator may describe a task in a compact way, but the robotic system needs much more information than the sentence explicitly provides. It must know which robots are free, which resources must be reserved, whether a route is available, whether an object exists, whether the task is individual or cooperative, and what should happen if a condition is not satisfied. Natural language is convenient because it is flexible and easy for humans, but that same flexibility makes it ambiguous for machines. Low-level scripts have the opposite problem. They can execute, but they are usually brittle, platform-dependent, and hard to inspect. CRLL-X is positioned between these extremes. Its purpose is to express missions in a controlled form that preserves human intent while producing an engineering artifact that can be parsed, checked, traced, and connected to execution components. The guiding question of the work is how human mission descriptions for multi-robot logistics can be transformed into an executable, traceable, and back-end independent representation. The paper answers this question through four main contributions. First, it defines CRLL-X as a controlled mission language, meaning that it is close enough to human instructions to remain readable, but restricted enough to be parsed reliably. Second, it proposes a layered architecture that separates canonical syntax, parsing, surface abstract syntax trees, desugaring, executable core structures, and operational semantics. Third, it reports a functional Python implementation, not only a conceptual diagram. Fourth, it includes reproducible technical evaluation through corpora, tests, notebooks, CSV outputs, failure analysis, and baseline comparison. The important point is that CRLL-X does not compete with ROS, planners, simulators, or controllers. It feeds them with a higher-level mission representation that is expressive, reducible, auditable, and deployable. This slide shows the kind of mission CRLL-X is designed to represent. The example reserves Dock 2, waits until an aisle is clear, and then runs a bounded parallel block. Inside that block, exactly 2 free robots jointly carry pallet 7 to the dock. while another free robot inspects Zone B. Several important ideas appear in a single, compact specification. There is resource reservation, conditional waiting, controlled parallelism, quantified robot selection, and cooperative action. In unrestricted natural language, these aspects could be expressed in many different ways, which would be difficult to parse consistently. In low-level code, the same mission would be verbose and tied to implementation details. CRLL-X keeps the statement readable, but gives it a canonical structure. That structure can be transformed into a parse tree, a surface AST, a desugared executable core, and finally, a sequence of semantic transitions over a world state. The architecture is important because CRLL-X is not just a grammar. It is a layered transformation pipeline. The first layer receives the mission request and may normalize controlled natural language into canonical CRLL-X. The second layer is the formal language layer, where the LARC parser constructs a parse tree and then a surface abstract syntax tree. The surface AST is important because it preserves what the user actually intended: selectors, priorities, reservations, execution modes, and constraints. The next layer performs desugaring and semantic checks, reducing expressive surface constructs into a smaller executable core. After that, the runtime layer can simulate or execute the core through back-end adapters such as Python Runtime, A-Star Planning, CapelliaSim, ROS2, or MQTT. Finally, the evidence layer stores tests, notebooks, CSV files, figures, and diagnostics. This separation allows each step to be debugged and validated independently. A central technical contribution is the executable core and its operational semantics. The surface language can contain rich constructs such as each, jointly, split by strategy, priority, reservation, and policy installation. However, executing every surface construct directly would make the runtime unnecessarily complex. CRLL-X therefore desugars missions into a compact set of core primitives: core seek for sequence, core if for decisions, core wait for blocking conditions, core act for executable actions, core par for controlled parallelism, core reserve for resources, and core policy for policies. The meaning of each construct is described by how it changes an explicit world state. That state includes robots, objects, locations, resources, policies, task queues, background branches, and logical time. This is why the semantics is operational. The mission means the sequence of computation steps it induces. This supports traceability, diagnostics, and future verification. The implementation matters because it shows that CRLL-X is not only an abstract proposal. The current core is implemented in Python around a compact route called compile and run. This route receives mission text and an initial state, parses the text with a LARC grammar, constructs a surface AST, desugars that surface representation into a core AST, runs the core over the symbolic world state, and returns the updated state. The implementation uses data classes to represent the ASTs, a transformer to map parse trees into typed objects, desugaring functions to reduce high-level constructs, and runtime functions to update the state. It also includes evaluation utilities that produce reproducible evidence. This design is practical for notebooks, smoke tests, demonstrations, and future adapters. Most importantly, it creates a clean interface between the language-level research and the robotic systems that may consume the resulting mission representation. The validation should be interpreted carefully. The paper does not claim that CRLL-X has already been validated as a full industrial robotic system. Instead, it presents reproducible functional and diagnostic validation of the mission language core. The evaluation includes several layers. The first layer checks parsing, desugaring, and symbolic execution of canonical CRLL-X cases. The second layer evaluates controlled language intent recognition. The third layer uses deterministic A-star grid planning scenarios to verify route feasibility. The fourth layer analyzes failures by diagnostic stage, distinguishing syntax errors, semantic resolution errors, and runtime infeasibility. Finally, the paper compares CRLL-X against direct scripting and planner-only routes. The corpus contains 130 CRLL-X cases, including 77 valid cases and 53 negative cases, plus 50 controlled language sentences and 50 planning scenarios. The value is not scale, but controlled evidence that the pipeline behaves consistently. The numerical results summarize the current functional maturity of the project. The implementation passes 23 unit tests. It evaluates 130 CRLL-X cases and detects all 53 negative cases at the expected diagnostic stage. It also reports 12 validation notebooks with stored outputs, which makes the computational evidence inspectable rather than only described. The success indicators shown here, such as valid parsing, execution, controlled language intent recognition, A-star planning, and CRLL-Sim dry run dispatch, all reach the expected value in the controlled evaluation. However, the interpretation must remain balanced. These results show internal consistency of the current core under the designed corpora. They do not prove real-world robustness in a warehouse. The comparison with direct scripting is also important. CRLL-X is not intended to be the fastest route. Its contribution is abstraction, traceability, diagnostics, and back-end independence. The baseline comparison helps clarify what CRLL-X adds and what it costs. A direct script is extremely fast because it bypasses parsing, AST construction, semantic checks, and trace generation. But that speed comes at the cost of lower abstraction, weaker diagnostics, and reduced portability. A planner-only route is useful for route computation, especially when the problem is to find a path from one location to another. But it does not capture the complete mission: reservations, policies, actor selection, cooperative actions, and mission-level intent. CRLL-X sits above these components. It introduces overhead, but it also provides a structured representation that can feed planners, simulators, and robotic middleware. The deployment route is incremental. The project first establishes language and evidence, then simulation through CRLL-Sim, and later integration through ROS2, MQTT, or other execution stacks. The contribution should be presented as an engineering research artifact with clear limits. On the contribution side, CRLL-X defines a mission layer between human instructions and robotic backends. It separates syntax, ASTs, executable core, and runtime semantics. It supports stage-based diagnostics, so failures can be associated with parsing, semantic resolution, runtime feasibility, or back-end dispatch. It also provides reproducible evidence through tests, notebooks, corpora, and generated outputs. On the limitation side, the current validation is still initial. CRLL-X does not replace navigation, manipulation, perception, control, formal verification, or safety certification. It also needs larger corpora, richer environments, and more extensive simulation and robotic trials. Future work should expand the semantics, add more back-end adapters, test deeper CRLL-Sim scenarios, connect to ROS2 workflows, and compare CRLL-X against real warehouse mission authoring processes. The closing message is that CRLL-X should not be understood as a robot controller. It is better understood as a mission-level executable representation. Its role is to turn mission descriptions into auditable engineering artifacts. It makes intent parsable by imposing a controlled language. It preserves traceability by keeping surface ASTs and reducing them into a compact executable core. It supports diagnosis by identifying the stage at which a mission fails. It also defines interfaces that can connect to planners, simulators, Capella Sim, ROS2-oriented deployment, and future robotic backends. The broader idea is that human intent must pass through structured semantic layers before it becomes reliable robotic execution. CRLL-X contributes one such layer for multi-robot logistics. Thank you for your attention. I will be glad to discuss questions about the architecture, evaluation, limitations, or deployment route.